In this video, you don't need to take any notes on it. The concepts that we're talking here are just for a bit of information, and this lesson is all about the future of technology and where we could go, some of the cutting edge stuff that we're toying with now, and things that you may see in the future. We're going to look at some of the top alternative energy sources for the future. This comes from the Futurism website, which is a really great website for really cutting edge high-tech science. And this was a PDF file that I adapted to create a lesson on for today's lesson. So space-based solar power is another concept. We've talked about solar energy so far, but 55 to 60% of all incoming energy doesn't make it through the atmosphere. In a space-based solar system, fleets of satellites with these huge solar reflectors or inflatable mirrors would be spread out, directing the solar radiation into these solar panels. Just like we talked about in an early video about those concentration setups where it's just surrounded by mirrors, we would do the same sort of thing but in space. In March 2015, the Japan Aerospace Exploration Agency, known as JAXA, revealed that they had successfully converted 1.8 kilowatts of electricity into microwaves, after which they were wirelessly beamed them a distance of 50 meters, proving the idea's viability. So this is something that we may have in the future. We may have these space-based floating around solar systems that are generating their own solar power rather than having them mounted on Earth. Human power is another idea. I've seen this in some of your projects so far, but some of the simplest way to generate renewable energy is through our own bodies. Devices now use much less power than before, and harvesting just a microwatt of electricity would be enough to power many small electronic devices. We could do this through our own movement, simply through wearing a special system that collects and converts it, or it could be a knee brace that has a hinge on it that every time we walk, it generates a small amount of electricity, things like that. It could be vibrational energy in a guitar string, or it could be as primitive as a treadmill or a bike that you pedal to generate electricity to do something else. Tidal power is another one where we have this sort of floating apparatus that move up and down as the tides go in and out, and every time it goes in or goes out it moves some sort of a machine, whether it's an actual turbine blade that as the waves push against it, it spins, or as you can kind of see in this example, it's almost like the fin of a plane that as the tide goes in and out it lifts and lowers the fin, which turns a bunch of gears and generates electricity as well. Hydrogen power has been talked about for a while, and there was a period of time where they were talking about hydrogen cars and it just didn't take off. Hydrogen is a colorless, odorless gas, and it accounts for 74% of the mass of the universe, so it's a very abundant resource. It is found only in combination with oxygen, carbon and nitrogen, and in order to use hydrogen we must separate it from other elements. Once it has, though, the gas yields a very high energy and produces almost no pollution, so it's a very, very clean fuel to be burning. Fuel cell devices convert hydrogen to electricity are already being used, and these provide power for vehicles, aircrafts, homes and buildings. So these can take things like water and they can split it into oxygen and hydrogen. They then burn that hydrogen and we've got our very high energy resource. Magma power is another concept. So tapping the magma deep within the earth, which again, as we talked about for general electricity production, we heat water, generates the steam and spins the turbines. 10,700 megawatts of geothermal electricity generated worldwide in 2010. So that's a lot. That's not using this power, that's just using the geothermal, which is just the heat under the earth. But in this case, we're talking about actually using the lava, so to speak, deep under the surface. Iceland's IDDP-1 is the world's first magma-enhanced geothermal system, and the first to supply heat directly from the molten magma. It's capable of generating 36 megawatts of electrical power. So we're using the Earth's molten core, its magma, to actually generate our electricity by heating our water and spinning the turbines. The next one is nuclear waste power. Only 5% of uranium atoms stored at nuclear power plants are actually utilized in the fission reaction. The rest are added to the nuclear waste stockpile. 77,000 tons of radioactive leftovers have piled up at America's nuclear power plants so far. Fast reactors, an existing technology, can be redeveloped to harness up to 95% of the energy nuclear fuels can generate. So this is really talking about improving the efficiency of a nuclear reactor and being able to use this waste and recycle it back through a reactor to get more energy from it. Embeddable solar power is the concept of turning any window or glass into a photovoltaic cell. So we've got these solar panels that we can embed within any piece of glass and we can still see through them. So every single window, car windshield, things like that, mirrors, etc., could be converted into solar panels so that we're harvesting huge amounts of surface area that we already have without these giant solar panels stuck on the roof. Algae power is another one that we're proposing, where algae is actually a surprisingly good source of energy-rich oil, and it can be genetically modified to produce the biofuel directly. Wastewater that hinders plant growth has been shown to be very effective in growing algae, so we can use all this wastewater, grow the algae in it, and we can have up to 9,000 gallons of biofuel that's grown in this area. Alabama in America has built the world's first algae biofuel system. It uses floating bioreceptors. Algae treats the municipal waste, and after it's harvested, the resulting clean water is then discharged into the bay. So the algae is actually purifying the water. We then harvest the algae to generate this biofuel, and we get a bit of a win-win. We're purifying water and generating a renewable source of biofuel. Flying wind power is the concept of conventional wind power, our wind turbines, but in this case it's actually flying, so we suspend it up in the air. This could be done through giant helium balloons, or we could just mount them up through sort of strings and things like that, but we get a lot more wind higher up. Closer to the Earth, the wind drops off, so at really high levels we can have up to 8 times stronger wind than we do at sort of ground or tower levels. The next one is fusion power. Fusion is the same process that the sun runs on. It has the potential to provide a nearly inexhaustible supply of energy. It emits no pollutants, no greenhouse gases, and it has no threat of nuclear meltdown, unlike the current fission reaction, which is what they use in nuclear power now. Fusion works by fusing together 2 hydrogen isotopes, deuterium and tritium, which are both bountiful, meaning there are lots of them available. So whereas in a fission reaction, it decays into other things, so one thing breaks into many, fusion, we take 2 things and we combine them together. This is something that we're still working on, we haven't quite perfected, and the ITER, or the International Thermonuclear Experimental Reactor, which is being built in France and funded by 7 countries, is set for completion by 2027. And this is the hope that it's going to be the first commercially demonstrated fusion power station. So it's currently not in existence. We've got the technology and stuff behind it, but 2027 is hopefully the very first time that we'll utilize fusion power. Another one is the Dyson Sphere. So this is a fairly sci-fi concept, but the Dyson Sphere is basically a sphere that is designed to harness the power of the sun itself. So it's kind of like building a giant solar panel that encases the sun, and every piece of energy that comes off that sun we harness through this sphere.
Human history is told by the energy we use. At first we had to use our muscles, then we learned to control fire. We industrialized the world using coal and oil and entered the atomic age when we learned how to split a nucleus. At each step, we increased our energy harvest to a scale never seen before and advanced as a species. Currently, we're slowly transitioning to renewables, and if we're lucky, fusion energy will become viable in the future. As humanity progresses further, if we don't destroy ourselves or our habitat, we will likely gain complete control of our planet's resources. At that stage, we'll probably begin to look outwards for new places to expand into. But space is hard, and establishing a serious human presence in the solar system will require ungodly amounts of energy. Luckily, we know where to find it. The sun, the ultimate source of energy. A furnace 100 quintillion times more powerful than our most efficient nuclear reactor. It shines with the energy of 1 trillion nuclear bombs per second. So how do we get this energy? Not some of it, all of it. If we want to collect the most energy physically possible, we'll have to build the largest, most ambitious structure in the universe, the Dyson Sphere, a megastructure that encompasses a whole star to capture its power output. For an intelligent species, building a Dyson Sphere is a technological leap on a par with the discovery of fire for our ancestors. The transition from a planetary species to an interstellar species. It would usher in an age of exploration and expansion on a scale we can barely imagine. So, what would it look like? A solid shell enveloping the Sun is probably not the way to go. A large rigid body like that would be vulnerable to impacts, possibly shattering. It would be liable to drift and could crash straight into the Sun. A more viable design for a Dyson Sphere might be a Dyson Swarm, an enormous set of orbiting panels that collect the Sun's power and beam it elsewhere. Such a swarm would give humanity basically unlimited energy. But building it won't be easy. The Sun is very big, so we need a lot of satellites. If each satellite is a square kilometre, we'd need around 30 quadrillion to surround the Sun. Even if they're built as lightly as possible, we need about 100 quintillion tons of material. And then we need the energy to actually put the parts together and deliver them to their positions around the Sun. On top of all that, we need to have a permanent infrastructure set up in space to start building. Let's assume, for the purposes of this video, that our descendants will take care of that and want to create the megastructure. We can sort the challenges into three main categories: materials, design, and energy. To get the vast amounts of raw materials required for our Dyson Swarm, we'll have to largely disassemble a whole planet. Of the planets available, Mercury is the best candidate. It's the closest to the Sun and very metal-rich. Close to the Sun also means less moving stuff around. And Mercury has no atmosphere and only about a third of the surface gravity of Earth, making it comparatively easy to launch material into space. Next, we should consider the design of our swarm. Simpler is better. Conventional solar panels are far too intricate and short-lived. Our satellites need to operate without repairs or intervention for astronomically long times, and they need to be cheap to produce. They're most likely going to be enormous mirrors, which refocus sunlight to central collecting stations, like in concentrated solar power on Earth. To build and launch them efficiently, they must be incredibly light, made of little more than polished metal foil bound to some supports. And last, we need the energy to build and launch the swarm itself. Taking apart a planet and launching things into space requires an enormous amount of energy. For example, if we used all the fossil fuels and uranium on Earth and we were perfectly efficient, we could only launch as much mass as Mount Everest into space. A rather meager accomplishment compared to planetary disassembly. To get the energy needed to build a Dyson Sphere, it's almost as if you're going to need the power output of a Dyson Sphere. But that's okay. There's plenty of sunlight to be had on Mercury, so let's get to work. Humans are expensive to keep alive and are very sensitive to the environment, so we'd want to automate as much as possible. Ideally, we'd have a small crew of controllers who oversee an army of autonomous machines doing the actual work. There are four major pieces of technology required: solar collectors, miners, refiners, and launch equipment. The solar collectors are going to give us the energy we need to disassemble the planet. To start, maybe we deploy something like 1 square kilometre of them, either as mirrors or as traditional solar panels. They'll provide the energy to run our miners, which strip mine the surface of the planet, and our refiners, which extract valuable elements and fabricate them into our swarm satellites. To get them into space, we need a creative and efficient solution. Rockets are too expensive and difficult to deorbit and reuse. Instead, we'll want to use a sort of railgun, a long electromagnetic track which launches our satellites at high speeds. Our swarm satellites would be packed tight for launch, unfurling like an enormous origami once in orbit. From this point, we can take advantage of exponential growth, using the energy of the existing parts of the swarm to build more infrastructure on Mercury and launch new panels faster and faster. Each panel provides the energy to build another. Those two work together to build the next two. 4 become 8, 8 becomes 16, and so on. Within just about 60 doubling times, the Sun would be completely surrounded by solar panels. And this can happen quickly. If a square kilometre of solar collectors takes a month to build, we could be done in a decade, if only our infrastructure on the planet's surface can keep up with the quickly growing budget of energy. Even collecting 1% of the sun's energy is an unbelievable change in our species' energy budget. We could create the infrastructure to beam basically unlimited amounts of energy around the solar system for all sorts of projects. Colonies on other worlds, terraforming planets, constructing more megastructures, or even travelling to other stars. It could be the start of an interstellar civilization. Based on physics alone, this is not just possible, but easy. It's such a simple process and such a necessary step for any species to expand beyond their home planet that many astronomers think there are probably Dyson Spheres already out there in the Milky Way. We haven't spotted any yet, but they could be there. It's far from certain that humanity will ever get to this point. Our attention is too often focused on short-term political gains and conflicts that will not matter in the long run. But if we survive the challenges we've set ourselves, we could potentially become the first species in the universe to create a structure with the scope of a star. If we do it, the only limitation left will be our own imagination.
It's interesting because it's a very sort of sci-fi style concept, but at the same time, the technology behind it is actually quite simple. It's really just those small challenges of getting the energy in the first place, being closer to the sun to be able to do it, and things like that. So it's not at all an impossible task. It's just a matter of improving our technology to the point that we can actually do it. And as I mentioned, we need every country in the world to collaborate together for this greater goal, rather than what we're kind of doing now is we're almost competing against each other to have more energy than someone else or have better technology and things like that. So when we look at some of the future energy topics that we've covered so far, we've got advantages and disadvantages. And you can see in the list there is a whole range of categories. So we've got reliability, air pollution, radioactive, safe for humans, environmentally friendly, not environmentally friendly, produces carbon dioxide, doesn't, non-renewable and renewable. So fossil fuel, we've got that reliable aspect, but we've got a whole bunch of disadvantages. Nuclear has its disadvantages and advantages. Solar, wind, and hydro. So there isn't really one that just has advantages and no disadvantages. There's no perfect answer here. In this video, this is a snippet from the 2040 video, and it's talking about microgrid energy solutions. So this is using basic solar power technology that we have now, but incorporating it in a slightly different method to generate power for civilizations and for small cities.
Just 20 years ago, these were the telephones most of us were using. Yet today, our phones are computers with more individual power than NASA needed to send men to the moon. The phone from 20 years ago is symbolic of our current energy system. But a revolution is on the way. Not only does our energy currently come from large centralised utilities that charge us some of the highest retail costs in the world, but we waste a huge amount of energy through inefficient appliances. The amount of energy wasted in the US in 2012 could have powered the UK for 7 years. In 2040, we explored the front lines of the energy revolution. In Bangladesh, any home with solar panels and a battery is given this box, which allows them to buy or sell energy with another home with the same setup. Together, the homes form a microgrid, which means they can generate energy independently from the main grid. And the money created from the buying and selling of energy stays within the local economy. Well, we think it's time to bring this revolution to Australia. And RedGrid is an Australian company who is making it happen. RedGrid has the ability to interconnect devices in your home, so energy is used more efficiently between them. This removes waste from the grid and saves you money on your electricity bill. RedGrid also has the ability to interconnect our homes and form microgrids, just like in Bangladesh. Although Australian regulations mean we don't have as many microgrids as we could have, this is rapidly changing. 2040 and RedGrid are inviting you to help Australia move from an energy dictatorship to an energy democracy. Red Grid are already working with communities, universities and energy organisations around Australia.
And we're opening up a crowd equity raise so that people who want to invest in this new energy model can actually invest in our company and take a share in where we're going in the future. And they'll also be the first people around the world to get their devices already pre-connected to the Internet of Energy. The time to fight climate change is right now, and it can start really with your old air conditioner. So come with us on a journey to create a new energy future for Australia and the world.
Head to the website today and join the regeneration.
Alright, so this concludes the video today on future energy. I hope you enjoyed it. There's some really interesting cutting edge and futuristic technologies that we're working on and we may see in the future.